Continue with the second session. Well, thank you very much to the authors. It's a great session. Today they will talk about in 4 different excellent papers about sustainable innovation, and the first contribution is by Albert Roger at the Max Planck Institute for Innovation and Competition. Albert, the floor is yours. Thank you.
No. Okay. Thank you very much. Well, first of all, thank you very much for the invitation. My name is Albert Roger, and I am a senior research fellow at the Max Planck Institute for Innovation and Competition in Munich. And it's a great pleasure today to be here in this magnificent venue to present you my work on estimating technological gains and losses from environmental regulation. All right, so first let me give you a short introduction to my work. So by now, as we've heard several times, climate change is an urgent problem. And in order to solve it, so we need to accelerate the sustainability transition and go beyond studying directed technological change and instead look at the rate of directing technological change. And for this, we need to study the drivers of that rate of directed technological change, and in particular, the technological gains and losses, or costs and benefits of directing it. So in this paper, I propose a method in order to estimate the technological gains and losses induced by an environmental regulation. And in particular, I'm going to show you also an application where I study the impact of an international environmental agreement, the Kigali Amendment to the Montreal Protocol, on the technology gains and losses. My work builds upon previous work from Paix 86 and Serrano 2018 on patent renewal models, but also on works on the Montreal Protocol, such as Barrett 94, Wagner 2016, and Dubois 2023, and works on the evaluation of clean technologies, such as Work in Progress of Martin and Verhoeven 2022. The main findings from my work is that the Kigali Amendment generated technological gains of up to 50,000 euros, average aggregate monetary gains for the patents of one cohort, and it generated little losses, and well, the gains are mainly concentrated on the most recent cohorts. So the main takeaways of my work are that, well, first, my findings support the rationale of Barrett 94 that, well, international environmental agreements are self-enforcing. That is that, they happen when the gains outweigh the losses. Then clean technologies seem to be undervalued. That is what the takeaway from my method. And that, well, if we want to accelerate the sustainability transition and the rate of directed technological change, then we need to make sure that people that have invested in clean assets, they get the benefits of investing in those assets. All right, so for the rest of the presentation, I'm going to first give a short overview on the method and the model, and then explain more in detail the empirical implementation. So for the method, I basically build a structural model of patent renewal, then I estimate. So the model is a patent renewal model that incorporates uncertain exogenous environmental regulation. And then I exploit the differences in patent renewal between clean technologies, dirty technologies, and the so-called control group ones, that are technologies that are similar to the dirty and the clean ones, but are not affected by the environmental regulation. And through this, I build a synthetic control and estimate the parameters of the model. So for those of you that are not familiar with patent renewal models, I'm going to shortly explain you the intuition. Basically, in these models, there is an agent that each period decides whether to renew or not a patent. For this, he or she needs to pay the renewal fees CA that are depending on patent age. And if they pay the fees, they get the returns of that age that are XA. And the discounted expected value. Then the returns from one period to the other are multiplied by a random shock that basically either increases the returns of the patent for, say, the engineers find new uses to the patent, either depreciate the returns by a certain factor, delta I, or make the technology obsolete. Then the patent holder, the technology, might become regulated. You have a patent on a dirty technology, and eventually, something happens and it's regulated. And then your returns on that period are basically multiplied by another random shock, GE, that makes your return either obsolete if you have a dirty technology, or increases the value of the returns of the patent if, say, you have a clean technology. Now, there are two main assumptions in this model. One is that the probability of being regulated is increasing over time, that is a probability PAT, that is increasing over patent age and across patent courts, but you start not being regulated, and then if you are regulated, you stay in that absorbing state, right? And the second assumption is that basically the agent is myopic to the environmental regulation. All right, so with this short and fast overview, in the interest of time, now I'm going to pass directly to the empirical implementation. So just to give you a short and fast overview on the environmental regulation. The Kigali Amendment to the Montreal Protocol was signed in 2016. So the Montreal Protocol is seen as the most successful international environmental agreement and aimed at phasing down and out the so-called ozone-depleting substances. And it regulated several groups of substances. The last one is the HFCs, that themselves, they are not greenhouse gas, they are not ozone-depleting substances, sorry. They are very powerful greenhouse gases. That is that one molecule of HFC has the equivalent global warming power of up to 100 to 1,000 times that of one molecule of CO2. And here you can see basically a graph with some simulations from Velders et al., where what they have just done some projections of the increase on the temperature increase that would have happened in the absence of the Kigali Amendment. So with the Kigali Amendment, basically we would have, by the end of the century, plus 0.05 increase. Without it, we could be at plus 0.4 degrees at the global scale. So when we are talking about this kind of international environmental agreements, the question is, what are we talking about? We are talking about phase-down schemes. And this is the example of the phase-down scheme of the Kigali Amendment, where basically there are two types of curves, those for the industrialized countries, those for the developing countries. And for the industrialized countries, we can see here that by January 2024, they could only consume 60% of the HFC's quantity compared to the baseline. So as I mentioned before, I have three groups of patents. So I have the clean ones that cite substances that could replace the HFCs. I have the dirty ones that are those that cite the HFCs. And then within each technology class, I have patents that are similar to those, but that do not cite these substances. Now, before presenting the results from the structural model, I'm going to first present some short reduced form evidence. Here is from a non-parametric regression model, where I present on the left graph differences in local hazard rates, and here ratios of local hazard rates between the clean patents, the treatment group patents, and the control group ones. And the way to interpret these graphs is basically that, well, I am assuming first that there is a shock in 2008 that is well before the regulation, and then it would capture any difference in hazard rate happening afterwards as a delayed effect. That is that if there would have been anticipation of the regulation, this would have been shown here, or if it would happen afterwards. And what we see here is that the clean technologies seem to have suffered a positive shock, so they were renewed in a higher rate compared to the control group ones already before, which makes sense because actually those substances, they were replacements for the substances regulated under the Copenhagen Amendment in '92. And then we see a positive shock on the hazard rate for clean substances in 2018. Now, when we look at the dirty ones, we see also that they were renewed in a higher rate compared to the control group ones, But then that in 2016, it seems that there is almost a negative shock in the hazard rate. So it is not significant, but it seems that they were slightly eventually affected. And this variation is what I exploit basically in my structural estimation. Here I'm presenting basically the second part of the structural estimation. In the first part, what I do is that I estimate the parameters for the control group patterns. So that are common basically for all groups. Then I plug in those parameters and do a second structural estimation, simulating the renewal for the control group patterns, and compute here the deviations out of it for the clean patterns and the dirty ones. So basically, here I'm running three scenarios. The first one, I assume that all patterns are treated in 2016. They are all affected the same year. The second one, I assume that the dirty ones are affected in 2016 and the clean ones in 2018. And the last one, I assume that, because eventually some people were treated before, other later, that the probability is just increasing over time. So summing up the results, basically I find that in the first scenario, there is no negative effect. I find that there is the largest positive shock on returns of clean patterns. For the second scenario, I find no effect at all, nor clean nor dirty, and this could be due to the functional form that I am assuming for the shock of the environmental regulation. And the last scenario, I find basically that there is a very tiny, it's a difference from 1 minus this number, actually the negative shock. It's a very tiny shock, which is similar to what we've seen in the reduced form evidence. And there is a shock on clean technologies, but it's not as large as in the first scenario. So almost to conclude, here I'm running basically some counterfactual simulations where I aggregate the returns of clean patterns and control of clean patterns and compute the differences compared to the control group ones. So basically, it's multiplied by the number of patterns, and we see here that the largest, so first gains seem to be increasing over time for the most recent cohorts. They are largest, of course, for the first scenario, which is the one with the largest shock, and those gains can be of up to 50,000 euros here for all the patterns in terms of average difference in present discounted value for the patterns of one cohort. So wrapping up, in this paper, I developed a method that allows to estimate the technological gains and losses engendered by an environmental regulation. It builds upon, well, the existence of a shock that I show with a duration model, and it combines a synthetic control group with two structural estimations to estimate the effect. There are two types of findings, one from the empirical implementation, where basically my results support the rationale of self-enforcing agreements of Barrett, 94, where the gains outweigh the losses of signing an international environmental agreement. Then the main findings from my method are basically that, well, clean technologies seem to be undervalued in the lack of an environmental regulation, is that if we want to accelerate the sustainability transition by increasing the rate of directing technological change, we need to make sure that people that have invested in clean technologies, they get the returns of those technologies. Thank you very much.
Thank you very much. Perfect timing. Thank you. Well, our second presenter is Anupama Sen from University of Oxford. Let me charge your presentation. Here, the second. Okay. Anupama, the floor is yours. Thank you.
Thanks very much, Rafael. I will try to be as efficient as Albert was. I'll do my best. Anyway, thank you very much, Rafael, and good morning, everyone. I'm Anupama Sen. I'm from the Oxford Smith School, and I'd like to present a paper which is sort of a collaboration between energy economists, that's myself and Thuraj Jamasp, and a growth economist, Parantap Basu, who is based in the University of Durham. So in the next 15 minutes, I'd like to touch upon all of these things, but I'll focus specifically on the model that we've developed, a very simple neoclassical growth model, which explores these three concepts, a circular economy, the net zero carbon target, and sustainable growth, and see whether they can be brought together in this simple growth framework and what the policy implications are of bringing them together. And this is work in progress, so I'll touch upon next steps, conclusions, and the limitations of this work as well. So to start off with a very quick context, just 3 points of context. One is to remind us of the net zero target. What is net zero? Everybody knows for any sort of global temperature target, there's a finite amount of carbon emissions that can be emitted into the atmosphere, and any emissions beyond this have to be removed or balanced through removal, so you get net emissions down to zero. And for the 1.5 degree target, I think there was a recent paper that came out a couple of weeks ago, which said we had, a couple of months ago actually, which said we had about 250 gigatons of carbon dioxide left in the carbon budget. So it's quite a critical problem. A second point of context, the stock of carbon emissions has continued increasing relentlessly in every world region. And the third point of context, at the same time, economies have become more efficient at producing output. So there is a divergence between the rate of growth in GDP and the rate of growth in emissions. But just because we're becoming more efficient doesn't mean that we're actually addressing the problem, because emissions have to fall at a much faster rate in order to get to net zero. So what do we do in this paper? We are very interested in the relationship between these three things: net zero, the use of resources by economies, and growth. And given that over 80% of global primary energy consumption today is from non-renewable energy, that's fossil fuels, it's unsustainable, clearly. One way to get to net zero is to replace all fossil fuels with renewables. We argue in this paper that it's not enough. Economies also have to adopt circular economy techniques, that's reducing emissions as much as possible, but also reducing waste and trying to recycle waste back into a form of renewable output. So the research question that we address in the paper is sustainable growth achievable in a net zero circular economy? So what we do in the paper is basically we establish a very simple neoclassical growth model which integrates these three fundamental pillars of economics: the net zero target in environmental economics, circular economy in resource economics, and sustainable growth, which is a topic in growth economics. And we try to explore the dynamics of these three pillars in relation to each other and their implications for policymakers. We present two scenarios: a passive policy scenario where policymakers have a fixed target on recycling, on emissions, on removal, and an active policy scenario where those targets are progressively becoming stricter over time. And then we see what results we get. Very quick recap of the literature. The first point to make here is traditionally the literature on these three areas have progressed separately until about the late 1970s. When they started coming together, and we saw some integration of the three concepts in literature. But the focus has predominantly been very much on sustainable growth and circular economy, and the net zero target isn't brought into the literature as much as is potentially possible. So I think the contribution of our work is to integrate those three things together and provide some insights on how net zero sits in relation to sustainable growth and in relation to circular economy. So introducing the model very quickly, we use a very, very simple model, an aggregate production function of a net zero circular economy, where we have two reproducible inputs. We have KR, which is renewable capital, and we have KN, which is non-renewable capital. And in this production function, we focus purely on production and technology. So we're abstracting away from the complications of the model, which is something we come back to perhaps in later work. We have ZT, which is the total factor productivity, and in equation number 2, we relate that to the stock of pollutants in the economy. So P refers to the stock of pollutants. And the intuition here is a higher stock of pollutants adversely affects total factor productivity. As pollution is brought down to zero, then total factor productivity reaches its upper bound. And by pollutants here, we refer to carbon-emitting pollutants, mainly carbon, but pollutants can refer to other things as well, like plastics, soil pollution, etc. As I said, this is a conceptual paper, so we're trying to abstract away from specifics in the beginning as much as possible anyway. So what do we do? What do renewables do in this model? Well, we assume that a fraction nu of the final output goes towards a stock of waste, which is W. And we assume that a proportion of that, theta, which is in just below equation 3, is recycled and converted back into renewable capital. At the same time, we assume that there's direct investment made into the creation of more renewable capital. And so in equation 4, we get a sort of a law of motion of renewables, where the stock of renewable capital, KRT plus 1, is equal to 1 minus delta R is the depreciation of the decay in the natural rate of decay and existing renewable capital, plus theta W, which is the proportion of waste that is recycled back into renewables, plus rho YT, which is the investment into renewables as a proportion of output. I promise there are just a couple more slides on equations and we go into the policy implications. We look at the same thing for non-renewables. So we look at how the time path of non-renewables evolves. And in this, we're saying a very simple thing, which is equation 6. So we say that as more investment is made into extracting exhaustible non-renewables from underneath the ground, the stock of renewables starts reducing in the economy. And there's a parameter IN, which is basically this investment that's going into non-renewables. But at the same time, we say that this parameter is determined by the rate of extraction, which is also a parameter which you can see in equation 5, which is xi. So 1 plus xi gives you the rate of investment into non-renewables. So this is also a policy parameter. So a government might decide to put limits on the extraction of fossil fuels or exhaustible resources, and it can be changed. And I'll come back to the policy implications later. So the dynamics of pollution is given by equation 7, where P is the stock of pollution. Here we have another parameter, which is delta P, which is the first term in equation 7. And delta is a parameter we put in there, which relates to pollution abatement. And it's also a policy parameter. So let's say a government mandates that a certain amount of abatement has to be carried out to reduce pollution. So the stock of pollution is determined by that, the abatement, plus the proportion of waste that's not recycled, which is 1 minus theta. And these two things together give us the total stock of pollution and the dynamics of pollution. So if we just relate this to the net zero carbon target, and coming back to the concept, net zero is reducing emissions as much as possible, but there's always a residual amount of waste despite that, and that has to be abated. So over here in equation 8, 1 minus theta WT is the amount of waste that is unrecyclable or hard to abate, minus delta P is the abatement. Delta is the abatement parameter. And we basically also introduce a pollution intensity aspect into this entire process, which is equation number 9, where we look at the proportion of the output that goes to waste and is not recycled, again, hard to abate, divided by delta P, which is the abatement parameter. And what this is saying here is, if you just take delta P, which is the denominator on the right-hand side of the equation, and you say a government mandates that all carbon is removed or abated from the atmosphere, so delta goes to 1, that's still not enough, because you still have 1 minus theta nu, which is the top term, which is basically saying that there's always a residual waste that cannot be abated, residual pollution that cannot be abated, and you have to have some form of recycling there or some form of getting rid of that. And that's where we make our key argument that the circular economy is a necessary condition for pollution abatement and net zero. And I'll come to this, come to what this means in policy terms as well. So that's our first proposition. And we also look at how this affects long-run growth, and we develop a long-run balanced growth path, which basically is defined as a scenario where the final output, which is YT, and the stock of renewables, which is KR, grows at the same rate, while the stock of non-renewables, which is KN, reduces. And there's a major policy element to this. Remember, I mentioned the rate of extraction psi. So for instance, the government could mandate a strict limit on the extraction of exhaustible resources. The government could mandate a strict recycling rate. And so we get a balanced growth rate, which is given by equation number 11, which basically tells you that growth is equal to the amount of abatement plus the amount of waste that's recycled plus the amount of investment that goes into renewables, which is rho. So those are all the equations I have for today, but I'll go quickly to what the implications or observations are of sort of drawing from this model. So basically, the 2 or 3 important implications here is that the greater the substitution between non-renewable and renewable capital, the higher the long-run growth rate. So the substitution parameter is very important. Secondly, the long-run growth rate is higher if the recycling rate theta and the investment rate in renewables rho are higher. And lastly, the long-run growth rate in a circular economy is much higher than in a linear economy. And so these last two bullet points are basically highlight the importance of a circular economy for growth potential. And we're saying in this paper that growth potential is higher in a circular economy, provided the right policy mix is adopted. I won't go into the short-run growth part, which we've also looked at. I'll come to the policy scenarios. So basically what we did was we tried to see how this relates to policy. What does it mean for policymakers? And we considered 4 policy targets: the net zero carbon target, efficient waste management or recycling, a sustainable renewable growth, and the time to convergence of an economy to a long-term steady state. We also looked at 4 policy instruments to achieve this. So a pollution removal or an abatement policy instrument, which is the delta P parameter, the rate of recycling, which is theta, the rate of extraction of non-renewable resources, which is psi, and the elasticity of substitution between non-renewables and renewables, which is sigma. So these 4 instruments are what we were very interested in, and we wanted to see whether they could be combined to give us at least the right directionality. Are things going in the same direction? So we're not looking at the values here, but rather the directionality. And so we basically assigned some values to the structural parameters. We assigned some values to the 4 policy instruments. And there are some limitations in the way that we assign this, which I'll come back to at the end. But then we ran those scenarios, and we basically found that things are going in the same direction. And the figure is too small for me to see from here, so I have a printout here. But basically, we simulated the GDP, renewables, and non-renewables, and we can see that GDP continues growing, renewables continue growing, and non-renewables growth slows down. We also looked at the growth rate of output and the growth rate of renewables, and we see both of them converge to a long-run steady state. We looked at the stock of non-renewables, which is declining, and we also looked at carbon intensity, which is also declining and reaches a very low level. And finally, we looked at the stock of carbon in this model, and interestingly, this continues growing. And we come back to this because we postulate an active policy scenario to deal with this issue. We also carried out some sensitivity analysis. So for instance, we looked at the sensitivity of the time to convergence to a long-run growth rate, to the elasticity of substitution between renewables and non-renewables. And in the table, it's the parameter sigma, and you see the higher the sigma, the quicker is the convergence to the long-run growth rate. Time period is in quarters, so this is 39 quarters, so it's about, let's say, it's 40 years, so it's about a 10-year period. But remember, this is purely conceptual, so we have to calibrate the parameters in a more efficient way. Second, we also looked at the sensitivity of the long-run growth rate to recycling. And as you can see, theta, which is the recycling rate, the higher it is, the higher is the growth rate. We also looked at sensitivity to the elasticity of substitution. Again, you can see sigma, the higher it is, the higher the long-run growth rate. And finally, we come back to that, to the graph I showed, where the stock of carbon continues to increase. And we say that here we need to adopt, the government needs to adopt or mandate some progressively increasing or stricter targets on abatement, which is the delta P parameter, and on recycling, which is the theta parameter. And we basically introduce those 2 things into the model and basically run the same simulations all over again. We get the same results in terms of directionality, but this time the stock of carbon declines right down to a very low level. So the main policy, the main results of this paper. So basically, to ensure a smooth transition, it is essential that the production technology allows for substitution. The higher the elasticity of substitution, the greater the growth potential when you move the economy from renewable to non-renewable to renewable capital. And the net zero carbon emissions can't be achieved solely with the substitution of non-renewable with renewables. It's a necessary but not a sufficient condition, and we find it's essential to have a recycling or efficient waste management or circularity within the economy to achieve long-run growth and net zero carbon and reduce the stock of carbon at the same time. Policy implications, well, we portrayed a passive scenario and an active scenario. A passive scenario might be one in which the government sets some sort of market target, like tradable pollution permits, to achieve a reduction in pollution. And a stricter sort of active policy scenario might be one where there's more stringent regulation. But the reality is that it's somewhere between those two extremes. So you might have some government incentives, but you might also have some form of regulation. And many countries, for instance, have introduced limits on new fossil fuel extraction. So that could be one way of achieving this target. But a key kind of conclusion, policy implication is that net zero emissions can be achieved faster with sustainable growth in a circular economy framework with active policy intervention based on four things. The first is increasing the elasticity of substitution between non-renewable and renewables. The second is increasing the rate of recycling. And the third one is abating pollution, increasing the pollution abatement rate. And finally, basically disincentivizing investment into non-renewables. So these four policy parameters. Now, this is my last slide. So what are the next steps on this? Well, this is a conceptual paper. We're bringing together these three concepts. We've devised this model. It's giving us results that go in the right direction. But the parameters and also the policy instruments that we set are sort of speculative. So we need to do more research looking at the literature to see what are the realistic ways of setting those structural parameters and of setting the policy instruments. So what is the actual rate at which non-renewable investment is declining? What is optimal? What does it mean for utility? So we haven't gone into these issues, and we haven't gone into the micro foundations or the welfare implications, because we're purely looking at the production technology at this stage. So I think that's the last slide. Thank you very much for listening. I'm sorry if I'm a little over time.
Thank you very much, Anupama. Thank you for your great presentation in 15 minutes. Now is the time for our third presenter. It's Mattia Guerini from the University of Brescia. The floor is yours. Yeah, I will. Yeah. Here, here.
Yeah.
Okay, perfect. Thank you very much. And can you also put the slides there? Okay, thank you very much. And thanks to the organizer for having me. It's really a pleasure to present my paper to this great audience. And the paper is co-authored with Giovanni Marin and Francesco Vona. And it's called Financing Constraint, Climate Policies and Carbon Emissions. So let me immediately go through the motivation. And the idea is that for the climate policies to work and to be actually effective, one needs to consider that crucially depends on how firms are going to react to the different policies which are available at the different governments. And in particular, how firms react in either changing their energy mix or in investing in new technologies which are allowed to do some carbon savings. And governments clearly have at their availability a plethora of policies, and they want to pick the most efficient one in terms that they can spend less and obtain the largest returns in terms of reduction of global pollutants. And what is typically less considered by the literature is the fact that firms are very heterogeneous, and depending on the policies, they might have heterogeneous responses to the same policy. And one relevant source of heterogeneity are the financial constraints, in particular if you take into account that CO2 saving technologies require a very high level of investment before getting the returns out of them. And therefore, the literature suggests two possible options out of it. On the one side, firms which are credit constrained, they find it more difficult to invest because they don't have the financial resources to pay for the initial investment. On the other side, there is the macro literature on the role of financing constraints and monetary policy, suggesting that these firms are very active as soon as the financial constraints are unleashed. And in particular, they are more sensitive to credit shocks. So this is what we try to investigate, to connect this macro industry literature together with the climate and firm literature. So there are already some studies on these topics. In particular, the closest to our study is the one by Goetz at the German Central Bank, and in which he analyzes reaction of US companies to a credit shock, in particular, a credit shock on long-term debt. So the shock that Goetz is analyzing is a shock that modifies the slope of the yield curve, so that firms which are highly indebted at the long term benefit the most, and firms which are indebted at the short term, they don't benefit too much from the policy. And by looking at this, it finds that firms exposed the most to the policy, they react by reducing their CO2 emissions. Another interesting paper, which is close to ours, is the one by Bijnens at the Central Bank of Belgium. And they use exogenous price shock, so they use an instrumental variable approach in order to derive energy price shock at the firm level. And they try to interact it with the financial constraint, and they find that the firms which are constrained, they are more vulnerable when an energy price shock arrives, and they decrease their employment more. So this means that, for example, in presence of a carbon taxation, financially constrained firms will also decline their employment, for example. And finally, we take this other example using the California market, in which the authors show that the climate policies may also kick back. In particular, here there is a local policy, and therefore this paper points to the importance of the coordination of policies also among different governments, because a cap-and-trade California policy had the effect of increasing CO2 emission, not in California, but for firms which had multiple establishments. Basically, they moved production from the establishment in California to establishment somewhere else in the United States, which were less efficient in terms of CO2 emission, and therefore they increased the pollution of the emissions of CO2. So basically, in this paper, now I think it's already clear, we try to assess this following question: how financial constraints affect the emission of CO2 for non-financial corporations in the manufacturing sector. And in particular, we want to see whether financially fragile firms are more or less environmentally reactive. So it's a fully empirical paper. And we use these data sources. We use a very rich data set covering the universe of French firms. These are administrative data set, basically starting from balance sheets from 2000 to 2019. And we basically collect the usual suspect variables which one want to get from balance sheet data. The advantage is that we can merge the balance sheet data with this AHA data set, which is a survey of 10,000 establishments every year, in which we know what are the emissions of CO2 by single companies, actually by single establishment, and then we can aggregate at the company level, clearly, and their energy use, the energy price by source. And now, it's not presented today, but we are also evaluating this other data set, which is another survey on the investment in green technologies like filters for the emissions of CO2 or water filters and so on and so forth. So how can we measure financial fragility at the firm level? I mean, the literature here, it's very rich. We know since the paper by Abad Fazzari and Petersen, which is a daunting task to measure financial fragility. And so what we do, we use a standard variable, which is approached very much today in the industrial dynamics literature, which is the debt-to-asset ratio, which is a measure of how much the firm is already indebted. And the problem is that this variable is endogenous, because it might signal that the firm has been capable of obtaining financial resources. I mean, if you have a high debt, it could be, well, you are already highly leveraged, so you are financially fragile, or you have been good as a firm to obtain financial resources. So this variable alone does not allow to assess whether a firm is financially constrained or not. What we are lucky at is that there has been a shock in the past 20 years especially. I mean, so in our time sample, there has been a shock to monetary policy which declined exogenously the cost of credit for all companies. And in particular, it was the lowering the interest rate until reaching the zero lower bound, so nominal interest rate at zero. And why it is exogenous? Well, because it was implemented by the central bank for completely different purpose with respect to the emissions of CO2. It was done to solve the financial crisis and the European government debt crisis. So it has nothing to do with CO2 emission. It is homogeneous because it hits all the firms at the same time, and however, it can have a heterogeneous effect on CO2 because firms which are highly indebted, they benefit the most from the reduction of the cost of credit. So then we use a simple difference in difference estimator. We use a two-way fixed effect regression where we interact the zero lower bound, which is a time variable. So starting from 2011, we get a 1 before the policy is off. And we interact it with the pre-shock, so DTA-I, it's the average of the debt to asset before the arrival of the zero lower bound. And also we average it over 2000 and 2010 in order to smooth out possible year-to-year variation into the firm level. And interacting a firm level variable with the zero lower bound, a time variable, we obtain the effect of the zero lower bound, so a shock to credit, shock to monetary policy, depending on the degree of financial constraints. Clearly, we control for firm fixed effect, time sector fixed effect, and we also include other control variables. What is our dependent variable? Until now, I already talked about CO2 emissions. So clearly, this is the most interesting variable we are going to look at. However, we are also going to decompose CO2 emission into different components. And so we have different dependent variables. We have different specifications of our model so that we can evaluate how firms react in terms of total CO2 emission, in terms of carbon content of production, in terms of energy intensity, and in terms of market size. And this is actually the main table of results that we are going to obtain at the aggregate level. So, for example, in CO2 emission, you can see a coefficient of, significant coefficient of minus 0.36. This means that going from a debt to asset from 0 to 1, so a change in 100%, which is way too much, reduces by 0.36% the DTA, because it's a log linear regression. So what we did, we actually computed the average CO2 emission in 2000, and we computed the marginal effect from a change of an interquantile range. So for a company which is in the first quartile of the debt to asset distribution and moved to the third quartile, the reduction of CO2 emission, thanks to the shock, has been of about 10%, which is a reasonable number, also considering all the estimates which are present in the literature. Then we also look at the components, and we observe that there are two components which are negative and one which are positive. So the one which is positive is value added. This is consistent with the macroeconomic literature. So as I told you before, credit shock, monetary policy shock, positive shocks, they have a positive impact on financially constrained firms. And in fact, these firms, they increase their market shares, they increase their market size. However, financially fragile firms, they react both by improving their energy mix, so given the same amount of energy, they produce less CO2, as well as by being more environmentally efficient, so using less energy in order to do the same amount of production. One might argue that this effect has been due to pre-trends, so variations in the companies before the arrival of the shock, and this is what we found with respect to CO2 to value added, and with respect to all the other four variables, apparently there is no positive trend before the arrival of the shock, which points toward our interpretation of the results. So if I still have 2-3 minutes, I will take the chance to also discuss the interaction of credit policies with climate policies. And this is what we do in a second exercise, because in our sample, we have some companies which are subject to a law which has been introduced in the European Union since 2005, which is the EU ETS. And the problem is that these companies are large, less financially fragile, and more energy intensive. So they are not a random sample into our total sample of firms. So what we do a coarse and exact matching protocol in order to find among the untreated firms, so firms that are not subject to the EU ETS, firms which are perfectly equivalent or as similar as possible to our treated companies, but they differ only in the treatment. And then we augment the specification, the baseline specification, with a triple interaction. And the triple interaction is the effect of the credit shock for companies which are subject to the UETS. And so if we get some significant result over there, it means that there is a positive combination between monetary policy and climate policies. And, well, this is what we find. We find, in fact, that treated, as you can see, the sample is way more reduced now because we only consider treated companies and the matched untreated companies. So the statistical power is a bit less relevant, but what we find is that still these companies, treated companies, after the shock, they reduce the CO2 to value added, and they do so by becoming more environmentally efficient in terms of technology. So they reduce their energy intensity. We also do the same exercise by splitting the samples. So we here only look at the treated companies, and we find that, in fact, these two effects are there, while for the matched companies, these two effects are not there. And so it seems that there is a positive combination between these two policies. We have many robustness checks. I mean, I'm not going to present them here. And let me just wrap up. And the wrap up, actually, if you want, is the opposite situation, because nowadays we are having a monetary policy which is becoming more and more restrictive, which means that this can limit the extent to which the transition toward the net zero happens for small firms which are also more financially fragile. So these are the perils of the current moment that we are living. I believe, and drawing from this paper, this is the intuition that we get. Thank you.
Thank you, Mattia. And finally, our last presenter in this session is François Cohen from the University of Barcelona. François, the floor is yours.
Okay, well, so this is a paper with Jose Reséndez, and it has received support from the World Bank, and it's entitled Devising Natural Capital Finance. So the starting point of the paper was that governments and major financial institutions have said that they want to take into account the environment better and use environmental statistics better. But at the same time, what we have seen is that there have been many challenges in doing this, from the technical challenges that some environment economists in the room may know better, to some political and budgetary constraints. So the question is, well, what can we do about it? And so we've looked at some of the recent developments. So I don't know where okay. And so what we see is that right now, I mean, so this has a couple of years, but about 90 countries have been making progress towards using natural capital accounts. There's been a standard that has been internationally accepted, and ever since this is like kicking up, and in the US especially, so over the past few years, there's been like a lot of developments. But at the same time, this progress has been quite uneven across countries, some countries doing a bit more than others. And even when the data exists, the problem is that it doesn't mean that it's being used. So you can have a lot of data, but if no one is picking up and no policies kind of like using this data, then it's a bit of a shame. And for that reason, what the World Bank had been doing is trying to understand solutions to kind of like increase take-up, and especially, so what they've been doing is to look at progressive implementation of the NCA, because it is costly, so you focus on the most policy-relevant environmental accounts, and you also do a lot of capacity building in countries so that people know these accounts better and they start understanding how to use it for resource management. So what we want to do is to try to understand it. In fact, well, the message about natural capital accounts was not necessarily the right one to start with. So in this paper, it's not really technical. It's about being the spin doctor for natural capital accounts and try to kind of like say, well, maybe you should use these statistics more. And so the old story that you may know is that if you want to do a good cost-benefit analysis, you need to have good data on all your costs and all your benefits. So what you want to do is to measure comprehensive wealth so that you are able to understand, well, if you have increases or reductions in environmental values of the assets that you are going to manage. And that's basically what we would call beyond GDP stories. So you don't want to only use GDP, you want to use other types of information. The problem with that message is that it didn't really came across because people are still using GDP, and maybe you could do things in complement to GDP and so on and so forth, but when you look at environmental wealth, it's a bit difficult to tie it directly to employment benefits or increases in income and so on and so forth. So it's not really easy for people to implement. So the story that we wanted to kind of like investigate was the story of financial alignment. Basically saying, you know what, you are going to make the right types of investment with this type of data because you're going to track what are your impacts and dependencies on nature, and this has environmental value. And as soon as you do this, you may create environmental accountability for financial institutions and for the people that are being financed, and this may be a story that has kind of like, let's say, a closer interpretation for decision makers, especially in the finance sector. So to look at this, so we have tried to develop this concept of natural capital finance, which would be the use of natural capital data for financial to make financial decisions, and we try to understand if stakeholders would be ready to implement this type of framework. So on the framework, so basically it would have three general tenets. The first one is the idea that we are going to operationalize this natural capital accounts and the environmental data that we have. The second one is that by operationalizing this, we are going to take into account risks and returns from having an impact on nature. And the final element is that this would create some form of accountability so that you have financial accountability for your impacts on nature, so now you're going to care a bit more about it. So these are the three main elements, and you can kind of like try to understand what are the actors and how these things are going to evolve. And basically, so if you put natural capital finance in the middle, it's some form of intermediary between these natural capital accounts and what would be the general objectives that countries and then companies have. So at the company level, these are like the natural recovery plans. So the question is how you're going to fund your natural recovery plans, what are your objectives in terms of reducing your impacts on nature, through different types of financial assets, and that's going to be done with natural capital finance. So, the question is, okay, so is this even feasible? So there is an opportune context to do this because financial institutions are increasingly interested in doing this. And not only are financial institutions increasingly interested in doing this, there are like frameworks that are being thought of to kind of like try to understand how you are going to make the link between the two. And then there is a regulatory context that is favorable to it because central banks and financial institutions are moving and pushing the way forward to ensure that this can be done in the future. So there is this opportune context, and at the same time, we have the tools that have been built within the financial sector to kind of like create this operationalization of environmental data. So you may know about green bonds. So these are like, I suppose, the most famous ones. So these are like the type of tools that allow you to kind of like finance the right types of projects. So this is kind of like your earmark, the projects are being green, and therefore you kind of like go along with them. There are other ways of like pushing for green investment. One is to try to understand, to disclose environmental risks. So you can have a risk-based approach to understand, well, this is a risky investment, in fact. So, and this may allow you to capture the bad ones, you know, the investments you want to divest from. And finally, there is these new types of tools that use key performance indicators. So you look at, for instance, forest cover in a country, and you're going to say, you know what, I'm going to invest in your country, for instance, and if you increase your forest cover, I'm going to reduce your interest rates. So this is the case of a sovereign sustainability bond. You have, most of them relate to companies, but we have seen the development of these types of investments. So we have those tools in hand. So, and so the question is, okay, so the tools exist, the people seem to say that they want to do that, what's the truth about this? And so in this paper, well, what we do is, well, we ran a survey, so with the help of the World Bank and with other data that we collected, we sent our survey to about 5,000 people. It was an online survey, so naturally we received much fewer responses, but we still received 600 responses, which makes it the largest survey ever conducted on these topics. And among the respondents, we have about 200 people that are directly either working in banks or central banks. And the question is, okay, so we want to interpret the results of this survey. And because there is a problem in the gap of the number of respondents, what we need to understand is how it could kind of create selection bias. So basically, I would be very much afraid that all the people that responded to the survey were people in this room that are very much committed to the environment and therefore care about this. And maybe the 5,000 people that didn't respond didn't care. So what we have done in this survey is that we have nagged people differently. So there are some people that haven't been nagged, and some people we sent reminders and reminders and reminders. And this allows us to understand if, when you're very motivated, you receive our survey, you really respond to it, are you going to be kind of different from someone that we had to nag 50 times before they answer the survey? And that allows us to run a sample selection model that will give us some idea of the direction of the bias in our results. So very quickly on the results. So the first one is that experts tended to agree that nature-related risks were insufficiently accounted for in economic and financial decisions. So the sample mean is the uncorrected sample mean, and the corrected mean is after we ran the sample selection model. And basically we tend to have like this kind of like agreement even when we take into account non-responses. At the same time as they agree, the beliefs about the severity of risks may vary. So depending if we look at respondents or after accounting for non-respondents and also across asset classes and different types of experts, there seems to be kind of like a disagreement about how bad the situation is. And a lot of experts are not familiar with what we want them to use, which is, so CA, this kind of like a structural norm, or they may not have worked with natural capital data, and natural capital may not even be important in their workplace. And we are talking about experts, so people that allegedly should be using those. And another thing is that even when they were familiar, they really didn't like the data. So they thought that there were like several flaws in terms of lack of granularity, or simply because the data was not updated frequently enough, meaning that, you know, if you want to have a policy relevant indicator that you're going to track and you have data every 5 years, I mean, this is not going to happen. And that more progress was still possible. So even though the data is not at the stage, they still thought that across all asset classes, we should be able to do more. So there seems to be a possibility to do more. And when we asked them more specifically about how they could do that, so that's the type of potential that we see. What we are quite surprised about is that they are not only saying that you should care about bonds, so the type of like instruments that have kind of like been around in the market for quite a while, but they also care for increases in equity, grants or guarantees, changes in how we deal with insurance or different types of tools. So to conclude on this, I think, okay, not really. I mean, that was a kind of like a big jump. We asked them about using natural capital data to create KPIs. And what we found is that there is an overwhelming majority of people that say, yes, you should do that. So they are happy with the idea of using this data to create new financial instruments, provided that we lift different barriers, and they are somewhere here. And so the main one being the data, and the other one being risk of greenwashing. So basically that you would use these instruments, but that the purpose of increasing environmental quality wouldn't be met. And there are several reasons why this could be a case. I'm not going to explain those, but we discuss this in the paper. So as to, okay, so there is some form of an interest. People are not so happy with the data. So what are the next steps if we wanted to implement natural capital finance? So the first one is to have some form of public stewardship of the data. So clearly we need to improve the statistics that we have, but we think that this is not the only thing that can be done, because it's about the combination of the data and the objectives. So at the same time as we increase the quality of the data and we ensure that it talks to financial managers, what we need is to also enhance the credibility of corporate net recovery plans, so that you have on one hand the data, but on the other hand the objective. And as soon as you have these objectives that are set, then you can like think of the type of data that you need to enhance your capacity of reaching those objectives. And the last element is that we are quite in favor in the paper. Maybe not everyone is, so it would be interesting to have your conversation about these sustainability linked instruments. So over the past 2-3 years, we have seen sovereign LSLBs, so countries designing these types of instruments, and this is probably a way forward, especially when you look at forest cover and specific types of instruments that could implement those. So thank you very much. That was all.
Thank you, François. Thank you to all the presenters. And now, as usual in these types of conference, we face this dilemma between questions and coffee. But please go ahead if Natalia, more questions? We have two here in the first two lines. And we will collect all the questions, okay, and then you will have time to. The second is Jose here. Jose.
My question was very related, was also for Mattia, was very related to this question of Natalia. I want to understand a little bit more the mechanism of this. No? The obvious is investment, but maybe there are others to explain the mechanism. And also, I think it would be interesting to analyze a little bit more the heterogeneity, to see what kind of firms, which kind of firms are reacting more, more pollutants or these kind of things.
Thank you, Jose. Then Laura.
Thanks to everyone. I'll just do two quick questions. One for their second presentation. I was very curious about whether you were planning to include a relationship between the circular economy interventions on policies and abatement, because one of the impacts of some of the net zero policies, at least in theory, is that they might also incentivize recycling, reuse, and that's something that seems to be treated separately right now in your model. Correct me if I'm wrong. The possible impacts, interactions between them. So I think that would be something to consider going forward. And then the other question I had was also on the firms, and I was wondering about whether you had also tried to get an additional data set, and this is really exciting work also, I agree, all of the papers, because it is also possible that you have omitted variables in that some of the firms that were, smaller firms that were more cash constrained were also applying and receiving other sort of government support in France during that time period, and there are other data sets that maybe you can look at to try to at least rule out that that's kind of something else that played a role in their activities and investments.
More questions? If not, I have, it's more a comment to Anupama paper, is that I think that you should consider as a potential extensions to the paper the inclusion of taxes and subsidies as policy instruments, and also because you have this convergence that could be very time consuming for many decades. The welfare implications is not only about growth, is the different policy strategies could have different welfare implications. And finally, I think that in your paper it was critical, this rate of substitution or this substitution between technologies, okay? And this is something that will, in some particular cases, will take time to build, okay? That we don't have right now the technologies to this substitution in some cases, but if we invest in them, we can have these technologies available in 1 decade or 2 decades. But in any case, great paper, very interesting. Thank you. Please go ahead and we will finish our session.
Okay, well, thank you very much again for the questions. Related to the investment, in fact, I didn't present the results, but we are already investigating on the second survey that we have. The problem is that when we merge two surveys, clearly the sample size declines even more because the surveys are not repeated every year with the same firms. But what we find is that investment is not significantly affected by the financial constraints, but we find that self-production of energy, it is, and total factor productivity. Because green investment in that survey are actually filters to air, but they do not conceive solar panels. Solar panels are considered only under self-production. So we want to look at total investment, maybe, which should catch up a spike, which is specifically dedicated to investment in solar panels. And we find that, so these companies become, on the one side, more productive, both total factor productivity and labor productivity increase, and they produce, they become more self-producers of energy. And in terms of heterogeneity, yes, I mean, this is clearly something that we want to do. I mean, already by splitting the sample between matched and treated gives some intuition. Then we have another group, which are the unmatched and the untreated. So these are very small companies, less productive, and the effects there, I didn't show the slides, but they are stronger with respect to the full sample. And finally, I come to the omitted variable bias of other possible type of supports. I mean, to our knowledge, there is no specific government intervention, also fiscal. We have looked a bit over that. I mean, also because both me and Francesco, we have been in France for several years. And apparently, there is no specific targeted intervention towards small and financially fragile firms. Or at least not any kind of variation with respect to the previous policies. But yes, I mean, as another robustness check, we try to change the policy. Instead of having the 0 for the zero were bound, we have the 1 for the quantitative easing, which comes actually 3 years after. The effect is a bit smaller in the magnitude, but all the significance is still there. Thank you.
Thank you so much for the terrific comments. I think on looking at circular economy and abatement together, that's great. I think we'll definitely do that because at the moment we're looking at those 4 separate parameters, sort of circular economy via recycling, abatement, substitution between the technologies, and limits on extraction. So thank you very much for that idea. And Rafael's comments, absolutely. I mean, we haven't looked into the welfare implications and micro foundations of, within this model. We're purely looking at technologies. And so that would be, we are actually exploring going into that by looking not just at the welfare implications, but also looking at things like the budget constraint and including a convex cost function for one of the equations to see, you know, who pays for this, how does it percolate through the economy, what are the variables that are the outcome variables. So definitely a very good idea. Yeah, I think on substitution, yeah, it's absolutely a critical parameter. And I think with this paper, we were trying to start those conversations. We were trying to generate some conversations amongst the policy sort of decision-making community on within these 4 things, what should they be doing? What can they do faster? What can they do to speed up the transition? And then the extension to that will be, what are the implications on welfare of different combinations of those policies? So thank you, that was great. And we will be looking into that as an extension to the paper, for sure.
Thank you very much to all the presenters. They have done a very good job. And now it's time for coffee. Thank you again.